All right. So, what are we doing today? Now, stoichiometry, this unit is all about comparing the initial products, the initial products, the initial reactants from a chemical process and being able to calculate the products from that chemical reaction. So, using what you know from the beginning to tell you what you have at the end. But before we can even do that, we have to be able to tie both of those things together. And one of the ways that those two things were tied together is with this idea of the mole. All right. Now, way back in the day during Avogadro's time, if you remember, when they were comparing gases, they referred to them as volumes. So it was like comparing the volumes of two gases. But that doesn't really seem to be a good way of comparing things, because you can't compare solids that way, or you can't really compare the liquids that way. It's not as useful as comparing gases. So the idea of the mole, this number 6.02 times 10 to the 23, the way this number showed up is by comparing the masses of elements and the masses of the atoms, right? So like the protons, neutrons, and electrons, by comparing them to the masses of the object, this number would keep showing up. That's 6.02 times 10 to the 23rd. And that kind of became known as the mole, right? And then the mole has had multiple definitions throughout the year. The most commonly accepted one is that the mole is this many particles, and those particles are equal to exactly 12 grams of carbon 12. So carbon 12 grams of carbon 12 will have exactly 6.022, I think it's like 14 times 10 to the 23 atoms. All right. Now this becomes the definition of it, but you can apply the same definition to any other element on the periodic table. So if we take a look at anything on the periodic table, it will give you the same amount of atoms, right? So carbon 12, this carbon right here, if you got 6.02 times 10 to the 23 atoms of carbon, it would have 12.01 grams as a mass. Same thing with nitrogen. So nitrogen would have a higher mass for the same amount of particles. So this way, the periodic table is now being compared to number of particles, and it makes it a little bit easier. I know it looks like a little bit dark. My lighting, I don't know. But the numbers underneath tell you how many particles there are. The mass of that number of particles. And this becomes very, very useful when we talk about chemical reactions, because in a chemical reaction, you can write it down as atoms reacting. So we have a number of atoms. So the reason why we use this mole is so that we can compare all of these different substances, because they all have that relationship where the mass underneath is equal to that number of particles. So since they all have that fundamental definition, it makes it easy to compare. All right, and that's the real importance of stoichiometry, and it's how we use it. Let's actually show. I think stoichiometry makes a little bit more sense once you actually begin to practice it, and then practice, and it's just one of those things you have to practice. So, for example, let's take a look at this problem here. Calculating the number of iron atoms. Well, if we got 4.48 moles, And the definition of a mole, so 1 mole of any substance, 1 mole of any substance is equal to 6.02 times 10 to the 23 particles of that substance. Now the type of particle we have is atoms. And then the type of substance we have, well, we have iron and atoms of iron. All right. Now, whenever you have a conversion factor, you can always flip it around, right? And the value stays the same, 6.02 times 10 to the 23. It's basically rewriting or multiplying by 1, because 1 mole is the exact same thing as 6.02 times 10 to the 23 atoms. So we use this conversion factor to help us solve the problem, because we want to get rid of moles, and moles goes at the bottom. And we want to find atoms, so the atoms go at the top. All right, and if we take a look at this setup, you'll see that the things cancel. The only thing left over is atoms, which is what we were looking for. And I'll just multiply these out. Now, some of you, you haven't learned how to put this in the calculator, but you should practice putting things in your calculator. And don't use your phone calculator. Please try not to use your phone calculator when you do these. Use your graphing calculator so you can get more familiar with it. All right. So right here, you get 2.69 times 10 to the 24 atoms of Fe. Now, you must always write the unit, and you must always write the chemical. If you had me in my previous class, I would take away 1 point for not writing your unit, 1 point for not writing your substance, but now I'm going to take away all your points. I'm sorry for being mean, but label your stuff, okay? Label your stuff, because or else it has no meaning. It has no meaning. All right, but that right there, very, very simple. It's all about looking at your units, just like dimensional analysis. Look at the units at the top, look at the units at the bottom. All right, now let's take a look at this little problem. At this problem, it's a little bit different. We'll start off. If we have 5.68 milligrams, but those milligrams, well, we don't really deal with milligrams. We deal mostly with grams when we're talking about the mole. So we know 1 gram, and then the M, milli, means 1,000. So we know 1 gram is 1,000 milligrams. All right. So now that once we have grams, well, now we can go to moles. All right. So we can go to moles. 1 mole is going to go on the top, and we're going to know we're going to need grams, but grams of which substance? We're going to need grams of silicon. And where do we get the grams of it? Do we get it from the problem? Do we write 5.68? No, because that's not the mass of 1 mole. The mass of 1 mole is always on the periodic table. So we look at periodic table, we find SI. SI is right here, 28.085. So we would put 1 mole is 28 point. Whoops, I think I might have gone a little too fast, but maybe I didn't. Point. All right. So now it looks like we got our little setup, right? But we are looking for atoms. We don't want moles. But what we do know is that 1 mole is always equal to the same number of particles, the same. And in this case, those particles are atoms. So we put 6.022 times 10 to the 23rd. And we say atoms. And the atoms of which chemical? Of Si. Let's double check our units. You see the mg here? Well, the mg's canceling out. The grams and the grams cancel. The moles and the moles cancel. The only thing left over is atoms. So this becomes the setup. Now, I know last year I let a lot of you use that little mole map where you go from moles to moles. In this case, no, no, no. I want you guys to really focus on the units. If you can understand the units, it will help you in more than just these types of problems. That skill will go into the other sciences, okay? So do not rely on those little mole maps. Try not to recreate it. Try to go based off of your reasoning. All right, so 5.68 divided by 1,000 because it's at the bottom, and then divided by 28.085 because once again it's at the bottom, and then multiply by 6.022 times 10 to the 23rd, and because it's at the top. So all of this is equal to 1.21 or 1.22 times 10 to the 20th atoms of Si. So here we have it. That is the number of atoms in the milligrams, right? Now, number of atoms, very, very important when we talk about chemical equations, chemical reactions, right? So very, very important that we're able to go back and forth between them. And I think this is it for this section of notes. Yeah, it is. What we're going to talk about is molar masses on the next the next section. Molar masses of compounds. Okay, but peace out, people.